This section 5.1 is the probability distribution for a discrete variable. Now, first thing we'll define here is a random variable. It's a numerical value associated with an outcome of a probability experiment. Now, the two primary types of random variables, or variables in general, are discrete and continuous. Now, a discrete variable basically has a finite or countable number of possible outcomes, such as the number of something. So let's say like the number of hits in a baseball game. You start with 0, go from 1, 2, 3, 4. In other words, the variable cannot take on any values other than those specific values. A continuous random variable is essentially an uncountable number of possible outcomes within a certain range of values, but you can't count all possible values. That's represented like on a number line. You may remember from algebra, if you sort of wrote an interval like where x is between 4 and 6, and we're talking about all real numbers, you can't list those out, but it theoretically means all values, infinite values between 4 and 6. Now, random variables that are often considered continuous are like time, height, volume, temperature, things like that. Even though, that measures of time, you're often looking at devices that show every minute or every precise amount, but obviously you could measure time in fractions. You could have something with the right kind of device that measures 9.367 seconds. Another example I like to use regarding, like say volume. Suppose you had a 20-ounce bottle of whatever beverage is in there. Theoretically, the value, the amount that's in there, can take on any number between 0 and 20. In other words, it doesn't have to be, let's say, ounces. Only 0 ounces, only 1, only 2, unlike the number of hits I did for the discrete. It could take, the right measuring device. It could be 11.385 ounces. Okay, so let's just look at some examples here. Okay, right now this talks about, this chapter will deal with discrete variables. In the next chapter, we will show probability distributions for continuous variables. Here it's only discrete. Now these examples are just asking if a random variable is discrete or continuous. The number of goals scored in a soccer game, be discrete. The number of home runs in a baseball game, also discrete. In other words, those are both countable measures, and the number of actually gives it away too. The time it takes to complete a baseball game, that would be continuous. Number of defects found in an automobile at a final inspection, that would be discrete, countable. Temperature of an oven at a particular time, it's continuous, even though the oven may only show whole number values. As you're warming up an oven, let's say as it's going from, for example, 300 to 400 degrees Fahrenheit, theoretically it's taking on all real numbers as it goes through that interval. It's not only jumping from one integer to the next. Now here's an example of a discrete one that's not just the counting one. Like this says if you a $5 even money roulette bet, which you don't have to know anything about casino gambling here. I'm going to do a roulette example here in a little bit. But the point is, in this outcome, there's only two things that can happen to you: -5, you lose; +5, you win. So that's basically discrete because it's not taking on a range of values between those. It's only specific amounts. So that's how you can have then discrete, where it's not just countable. All right. Let's see. Amount of liquid in a 16-ounce bottle. Okay, I've talked about liquid. That's continuous. The number of questions answered correctly on a multiple choice exam with 20 questions. That would certainly be discrete. All right, so that kind of warms us up and gives us the idea of what discrete and continuous basically are. So let's jump down here and talk about constructing discrete probability distributions. A discrete probability distribution lists the value of all possible numbers that you can get for a random variable for a particular experiment, probability experiment, and then the probability, P of x, is the probability of that particular x occurring. Let's start with a couple of basic examples here. I'll start with one for sure. Let's say you roll a single six-sided die on your standard die cube. Okay. And let x be the number of dots facing up. So here we have our, there's a single six-sided die right there. And since x has to be numerical, the number of dots facing up. So on that six-sided die, the x's, we list them all out, 1, 2, 3, 4, 5, 6. So the probability distribution, then you would list the probability of each particular value occurring. And in this case, they happen to all be equal, and that's not always going to be true in a probability distribution. But in this case, it would be. Each of them has a 1 out of 6 chance occurring. So 1 out of 6, 1 out of 6. So yeah, don't ever make the false assumption that those probabilities are equal every time you do these, and we will certainly see some where they are not here shortly. And the basic discrete probability distribution must satisfy the two following conditions. Now, one of these you would have seen back in finite math is that the probability of any particular outcome has got to be a number between 0 and 1. You know, it could be 0, meaning it has no chance of occurring, or it can be 1, which is 100% chance of occurring, or somewhere in between there. So you can never have a probability problem that gives you a negative number or anything more than 1 and 1.2. And then the second condition for this distribution is the probabilities must all add up to exactly 1. So that's important also. So it means basically you're saying you have exactly 100% chance that individually one of those outcomes is going to occur. Okay, so here's some distributions I've just written out here, and we're trying to determine if they're valid or not. Now, keep in mind there are no restrictions on the x here, so that's the fact these x's are negative, that's all right. The x's have no restrictions. In fact, I already talked about the negative 5 for roulette earlier. So that's, yeah, x can be negative. We're only interested in the probabilities. Well, you look at those four probabilities, they all look nice individually. They satisfy the first case into 0 and 1. But as soon as you add them up, you get 1.1, which is not 1. So therefore, that's not a valid distribution. So whatever that was supposed to represent was not correct. Second example, all the probabilities are perfect between 0 and 1. They add up to exactly 1. You see I have the box over here. So that's what we would call that a valid distribution. Being valid doesn't mean for a probability experiment that it's correct. It just means that it doesn't fail one of those conditions. In other words, I'll talk about one here shortly that, yeah, you could still satisfy those conditions and be wrong. But at least if it doesn't satisfy that, you know for sure it's wrong. Now the next one, you see there's a negative probability, so that's game over right there. And I decided to make them all add up to 1 just in case somebody only checked that. You know, if you just check they add up to 1, you might think, hey, that works. But no, we've got a bad probability value right there. That cannot happen. Now here's a given probability distribution. Don't know what it's supposed to represent or whatever, and I just verified over it. Well, I didn't write the first condition. Maybe I should have put both of them in there, but I figured that was easy to visualize, so I'll go ahead and copy that down there, though. That one's obviously easier to eyeball, that it's between 0 and 1. And then but the other ones, you'd have to kind of add them up. Let me shrink this down, move this down here. So it's valid. All right. So let's ask some probability questions based on this distribution. Copy this. rid of that. All right, so let's test our ability to, read inequality symbols properly. So this first one says find the probability that x chosen at random between 1 and 3, but you see you have equals at both of these. So equal at 1, equal at 3 is the same thing as saying the probability of 1 plus 2 plus 3. So you add up those three probabilities that go with 1, 2, and 3, and that would be your answer. Add them up, you get 0.61. Now look at the next one. I have 1 and 3 again. I have the equal at 1, but I do not have the equal at 3. So what does that mean? Okay, that means we include the 1, but we do not include the 3. So it's just the probability of 1 plus 2. So you add those two up and get 0.29. Between 1 and 4, with no equals, that would only be 2 and 3, because you cannot include 1 or 4. So you add up 2 and 3, it's 0.8 plus 0.32, it's 0.40. Less than or equal to 3 means we would include 3. So you add the 3, 2, 0, 8, 2, 1, you get 0.61. Greater than 3 means anything above 3 but not 3. So we'd add up 4 plus 5. 17, 2, 2 is 39. Probability that x is greater than 5 would be 0, nothing there. And then probability less than 6 would be all of them, which would be 1. I probably wouldn't ask these two on a test, but I just kind of wanted to show there because of this rule right here, how they can equal either 0 or 1. So I just wanted to show an example of it being 0 and 1, just so you can see. All right, let's move down and see what's next here. Okay. Oh, never mind. Find the missing value to make this a valid distribution. So what we're going to do is, so the original problem would not have had this pink value. So we're saying, what will we need to make that fit in there to make it valid? Now, it's possible it might not be valid, but obviously if it's indicating that valid, there probably will be a number. So we have to use the property of knowing that they all add up to 1. So all we have to do is add up the other 3, 13, 2, 4, and 4, 7, and go 1 minus that, and that will fill in our missing number, 0.16. And of course, obviously, you can double check that. Add those 4, you see they're all good probabilities individually. Add all 4 of them up, and you'll get exactly 1. So basically, it's 1 minus the sum of the others. Now we're going to do a coin flip. So you may remember this from finite. 2 coins, HH, HT, TH, and TT would be the sample space. And but in this particular idea of probability distributions, we talked about up earlier that the random variable x has to be countable, something numerical. So we can't use H's and T's. So there would have to be a way to set up a distribution to where it uses numbers instead of letters. Okay, we can do that. Is by saying, what if we say let x be, and you can pick either heads or tails. We'll just go with whatever I pick, which I have right there. Let x be the number of tails in this distribution. Okay, so that way you see that we can make, it would certainly be countable then. So we can't use H's and T's, but well, we're good on, so x is number of countable. So if you flip a coin twice, and you're going to count the number of tails, and you're going to write down the answer every time you do it. You're going to do it over and over and over. Well, the only possible answers you can get are 0, 1, or 2, meaning you can get no tails, you can get 1 tail, or you get 2 tails. Those are the only possible answers you could have here, 0, 1, and 2. I mean, you're not getting 3 tails if you're flipping it twice, and you're not getting negative tails. I just drew a little flow chart. kind of going back to finite, that shows, well, now I've got some room here. Let me move this over. Maybe I can actually get the flow chart up there next to the outcomes. For 2 coins, it's not too bad, but listing out that tree diagram could probably be helpful if ever needed to do 3 or more. And now, so using that sample space, we have 4 outcomes up there. That tells you the total number sample space. So you see I listed my 3 X's. And 0, 1, and 2, and I want to figure out the probabilities. Well, the probability of getting 0 heads, there's 4 outcomes, 0 tails, well, obviously it's the same answer either way, but would be HH. 1 outcome out of 4, so it's 1/4. Now the probability of getting 1 tail, there's 2 ways to do that, HT, TH. 2 out of 4, I just didn't bother to reduce the fraction. Makes it easier to add them up. And then 2 tails would be the TT outcome, 1 out of 4. So each of those probabilities are fine, and if you look at them, you add them up, it's easy to see if they're 4 over 4, which is 1. That's what I was talking about a few minutes ago. It is valid, and this one actually is correct, but just to give you an example, suppose somebody wrote 1/3, 1/3, 1/3 right there for this experiment. That would be a valid distribution, but it would not be correct. So being invalid certainly is wrong, but being valid is not automatically correct. But this one's correct. Okay, here's one. Let's say I just took some table tennis balls, put a Sharpie on them, wrote down numbers, and I just wrote the frequency distribution over here, but you can kind of ignore that. Just come right down to here. So there's 10 of them. I wrote 2 1s on there. I wrote 3 2s. I wrote 5 3s. And so then the value 1 would have a 2 out of 10 chance because there's 2 1s. 2 would be 3 out of 10, and 3 would be 5 out of 10. Now let's talk about the mean of a discrete random variable, basically the average. Another way to think of it for a probability experiment would be the average for the long-term outcome. If you repeated over and over and over and over. It's also the thing, in this case, if you just average those 10 numbers, you're going to get the answer to this. But it's basically, it'd be if you did this over and over, large, millions of times, and averaged your results, you should be very close to the theoretical average. So this, if you average those 10 numbers up, that tells you the precise average. But what if you actually did the experiment yourself about 1 million times, which would be pure torture, but that average should be close to whatever the precise average should be. So you're using mu, because this is a population, not a sample. Real easy to calculate. You just take x times p, meaning you take each x times its own probability, then you move over. X times p, move over, x times p. You just do that until you run out. So I just roll like x1, p1, x2, p2, until you run them all out, and that's it. Pretty straightforward calculation. So for this one, you would go 1 times 2 over 10, plus 2 times 3 over 10, plus 3 times 5 over 10, and we have a mean of 2.3. Let's talk about expected value. Now, expected value is, calculation-wise, is the same as the mean. It's the same calculation. But we generally use the phrase expected value. It's okay, you can use expected value anytime you wanted to, actually, but we generally use expected value if it's going to be a problem involving monetary amounts or something like that. That's usually a good time we call it expected value. Meaning, on the long term, for something involving monetary things, what should be our average gain or loss per each time we do it. So in this case, now the random variable x are going to be, in other words, net gain, loss, amount. So now we're going to see some negative x's, because if you have some outcome where you lose money, that's going to be negative. So let's say we have just some sort of short-term business adventure with a probability of 1 over 10 that we profit 12,000, 4 over 10 that we break even, and 5 out of 10 that we lose $3,000. What is the expected value of this venture? So this, you got to be careful. Being business majors and taking accounting, this probably won't trick you up versus someone that doesn't have a business background. But what you have to realize here when you see the word losing 3,000 is that you have to treat your variable X as negative. So even though it doesn't have a negative sign next to the number, the word losing makes it negative. So here's the first one, 12,000, with a probability of 1 over 10, 0, meaning we break even, with a probability of 4 over 10, and then the negative 3,000, I was explaining we have a 5 out of 10 chance. So you just take each XP, 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 12,000 times 1 over 10, plus 0 times 4 over 10, minus 3,000 times 5 over 10. We get an answer of negative 300. So, okay, what does that tell you, that negative 300? What that tells you is that if you were able to just, whatever this venture is, that you could repeat it and do it over and over and over and over. It was a repetition thing. In the long run, in other words, you should lose about 300 per every time you do it. So after about 1,000 times, theoretically, you should be about 300,000 down. That doesn't sound too promising to me. But that's the long run theoretical average. What if you try this once in the short term and hit the 12,000 and you quit? That kind of thing. You can always stop in the short term. But this would not be a good venture in the long run. Not when it's a negative expected value. Okay, there's what I was just saying. Here's one I copied from an old textbook we used to use in this class. I wouldn't worry too much about it. I don't know what's the precise definition of no oil, some oil, much oil. But these numbers were already given to you in the chart. You didn't have to interpret them like I did in the last problem from the wording. So that makes it better. It's not, that way you don't have to worry about what no, some, and much means. But anyway, so they're telling you negative 40,000 means you hit nothing but dirt. You got a 0.25 chance of doing that. $10,000 profit, we got a 70%, 0.7 probability of that. And we've got a 70,000 profit, 5% chance of getting the much oil. So those probabilities add up to 1. That's good. Expected value, negative 40,000 times 25, 10,000 times 0.7, 70,000 times 0.05 is plus 500. So that 500 represents the average amount per drill in the long run, which at least it's positive, so that's good. But you still might not want to do this because one thing to keep in mind is you got to think about how much investment you have, how much bankroll you have, so to speak. Because this means this is how you should do in the long run on average. But depending on how much money you have there, what if the first 5 or 4 or 5, happen to be where you hit the no oil and you spend a lot of money there? You would hate to run out of money before you started realizing the positive gains that you potentially you should get in the long run. So that's always a factor, but that's something you don't have to worry about. I like to always mention that when I teach this. But at least positive 500, you would consider it over that negative 300 we did in the other example. You definitely wouldn't want to do that. Okay, here's a roulette wheel. If I ever use this as an example or use a test question, I would absolutely define this for you. You would not be expected to know that. And let's say we're going to bet $5 on black. So I would tell you that, okay, that means an even money bet. There's all kinds of things you can bet on that table that actually pay odds more than just even money. In fact, if you bet one number, they'll pay you 35 to 1. But obviously that's very hard to do. So we're going to bet black. We decided, okay, 5 on black. So there's only 2 outcomes here. You either lose $5 or you win $5. There's no other outcome. So now we have to figure out then the corresponding probabilities of those 2 things happening. Losing $5. So we look at this distribution of colors here. We lose if either red or green appears. Those aren't our friends here. So if red and green appear, that's 18 plus 2. That's 20 ways to lose. versus 18 black, 18 ways to win. So we have a 20 out of 38 chance of losing. We have a 18 out of 38 chance of winning. And notice that, just double check. You see, I made a note about the probabilities adding up to 1. That's certainly good to check because, what if you just, let's say you accidentally wrote, you got the greens and you wrote 18 out of 38 and 18 out of 38, and you just look at that only, then you could add those up and go, oh, that's 36 out of 38, so obviously I'm wrong here. What am I missing? And then you could figure out the greens. So this expected value would be negative 5 times 20 over 38 plus 5 times 18 over 38. So on a $5 bet, you should basically lose about 26 cents per outcome. But, if you're in a casino having fun, play roulette for a little while, it's not going to be that bad because it's not like you're going to be able to sit there. Yeah, if you did this a million times or something, yeah, you're probably going to lose about 263,000 times dollars. But who's going to do this a million times, But it's fun to play there a little bit. You might win in the short term. People do win in the short term. It's just the casinos are designed to have people lose in the long run. Or not necessarily individuals, just enough combination of winners and losers where there's more losers than winners. That's the key. And then they win. So, but it's a fun game in the short term, but don't think you're going to become a professional roulette player anytime soon. So, and I just kind of wrote this out as a percentage. I would never ask this on a test, but so when gambling books and articles and stuff talk about roulette has a house advantage of 5.26%. So in theory, that means of all monies wagered, not necessarily by one person, all money coming in, they should theoretically in the long run collect about 5.26% of that. Sort of as their fee for running the game, I guess you might say. But now here's one where I made up a card deck. If we need the card deck, I would certainly give you this. I would not expect you to know that. I would provide that. But you probably remember that from your finite days. Hearts, diamonds, spades, clubs. Sounds like a box of Lucky Charms cereal. Okay, hearts, diamonds. This was 18 reds, 18. Oh, they look pink, but they're red. 18 red, 18 red, 18 black, 13 of each suit. So let's say these two people are playing a game against each other. And anytime you've got what they call a zero-sum game is whatever your expected value is, that means the opponent has the opposite. So another way to look at it, like going back to that roulette example, the players have a negative 5.26% advantage, which obviously then is a disadvantage. That means the casino has a positive 5.26%. So it's just the opposite sign. So we're going to look at this from Wendy's point of view here. What would be her expected value? And that means Cecilia's would just be the opposite of that. You don't have to redo the calculation. So Wendy's going to draw. Cecilia's going to pay her $2.50 if she draws a heart, and Wendy will pay Cecilia $1 if she does not draw a heart. So it's either heart or not a heart. What is Wendy's expected value? And then I just abbreviated here. So what is Cecilia's expected value? So Wendy's plus 250. She has a 13 out of 52 chance of that happening because all these 13 hearts work in her favor. But she's a negative 1 outcome of losing $1 if any of the other 3 columns appear, any one of those 39 cards. So you do the calculation, and it's negative 0.125 for Wendy and positive 0.125 for Cecilia. So that means on average in the long run, Wendy should lose 12.5 cents per play. That's in the long run. So obviously the idea, for Cecilia is she would like this game to be played as long as possible because it will work to her advantage. But in the short term, anything can happen because, for example, Wendy could draw the heart like 4 times in a row, and collect 4 times 250, collect $10, and say nice doing business with you. So, but the longer the game is played, the person with the positive expected value absolutely will win. And so that's what they mean by winning in the long run. All right, here's one car wash. You lose $30 on a rainy day, and you make $120 when it doesn't rain. and the probability of rain is 0.15, what is the car wash's expected profit basically per day? So we have two outcomes, negative 30 and positive 120. Notice they only gave us one probability value. That's okay, because if there's only two outcomes and they give you one probability, that means the other probability would have to be 1 minus the one they gave you. But obviously they could not give you, if there were three outcomes, they could not just give you one probability. They'd have to give you two probabilities. They can always give you one less probability than you need, because you can always do the 1 minus deal. So if you got a 0.15, so negative 30, you lose $30 with a 15% chance of rain. And then you make 120, and then if it's a 15% chance of rain, it's an 85% chance of not raining. So there's where the 8.85 comes from, expected value, pretty easy calculation when I do that by now. So you'll end up positive 97.50. So they should have that should average 97.50 per day profit. All right. So let's see what we got going on here. Now, all right. The next one's a little trickier because you have to, the way you figure out the profit, the way the wording of the question is. But I have confidence in you. Yeah, I guess I've got a lot of empty space there. That's okay. Now, I changed the wording on this. I didn't like the word make. I changed it to receive. Lawyer believes the probability that is 0.3 that she can win a discrimination suit. If she wins the case, she receives $40,000 for winning. But if she loses, she gets nothing. Assume that she spends $5,000 preparing the case. What is her expected gain? Now, there's a couple ways you could do this. I could have probably done this by going, well, I'll talk about that here in a second. I think it would have worked the same way. So there are two ways to do it, but I just chose to do it this way. I chose to look at it as if she receives $40,000, that's not pure profit. That's revenue, I guess, for you business folks there. So if she's spending $5,000 no matter what, so she really only gains $35,000. So she has a 0.3 probability of gaining $35,000. And then if you get nothing, that's you really lose $5,000. So it's a negative $5,000. You got a 0.7. Once again, they gave us one probability, so 1 minus will get you the other one. So if you do the calculation like this, you get 35,000 times 0.3 minus 5,000 times 0.7 because of the negative, and you get positive 7,000. So she should profit 7,000 per each time she has one of these cases on average. Now, another way you can do this, but I didn't show you that really way in the notes up here, so that's why I didn't do it. But if you put 40,000 here where the 35 is, and you put 0 where the negative 5,000 is, you can just subtract the amount 5,000 as a whole number at the end. Because if you put 40,000 and 0, and you do the expected value, that'll come out 12,000, and then you can just subtract the 5,000 at the end and still get 7,000. So that would also work. Now, the last thing in this section is variance and standard deviation of a random variable. I probably won't do every example here. I didn't in person. So, but it's just a plug and chug formula. That there's no, unlike these last couple of word problems, there's no having to think too hard about setting this up. Once you can perform the formula, you're good. You know, it's nothing word-wise, in other words, that makes it tricky. Variance and standard deviation. So we have two formulas for this. Number one and number two, I call number one the kind of the shortcut formula, like we've had that before when we did variance and standard deviation for individual numbers. One of them. I like the one that doesn't. Same thing here. I prefer to use the formula, but you do whatever you want. But I prefer to use the formula that does not do all these subtractions right here, where you have to go x minus mean, x minus mean, x minus mean. There's only one subtraction. However, unlike the shortcut formula before, where you didn't even have to have the mean to do it, you do here. Either way, you've got to get the mean first. And that's from this formula we've already seen. Unless the mean was given to you, but if not, you have to go xp, 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 and calculate the mean, because you need it whichever formula you're going to use. All right, well, this is the variance formula. Variance always has a square, and we're using this is the population because it's not a sample. So it's the sigma squared. And as I've mentioned before in other sections, that this is the same rule at all times. The standard deviation is always the square root of the variance. Always. So, yeah. So once you have the formula calculated, all you have to do is square root it to get the standard deviation. So here's just a distribution that I made up. Made up 5 x values, made up the probabilities, but however, they still have to be in the guidelines of adding up between 0 and 1. Adding up to 1, excuse me, and each value is going to be between 0 and 1. So you can check that to make sure. And of course, I wouldn't give you one on a test that didn't, but I think if you add that up, 406192 plus 8, 100.4 is 1. So obviously this needs to be valid. So I'm going to do this using that formula in red. That's the one I like better. Where we go x squared times p, add all those up, and then just subtract the square of the mean. So the first thing I'm going to do is I'm going to get the mean. I did right here. So mean is just your standard xp, 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 xp. Add them up, and you get 8.4. So there's the calculation for the mean. And to use that formula that I called number 1 up there, and the one I copied right here, you square each x. So 2 squared is 4, 5 squared 25, 8 squared 64, so forth, so on. You square those, and because now we're going to be multiplying right here, x squared times p. So notice that, so what I have down here, I have x squared times p, so it's 4 times 0.2, 25 times 0.28, 64 times 0.21, 144 times 0.31, 289 times 0.08. And so you just have the same numbers I just said are all right here, but you got to be careful because you might think if you just go x squared p, and add those up, you might think, hooray, I'm done. That's it. That's not it. One little piece you got to do here at the end. You have to subtract the square of the mean that we got right here, the 8.4. So you do the, x squared p, blah, 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 add that up. I guess I didn't. Well, here it is down here. Didn't know if I'd put it in the calculator box or not. There it is. But then you have to subtract minus that 8.4 squared, so we don't want to forget to do that. So the variance is 18.12, and then the standard deviation would be the square root of that number, which is roughly 4.26. And then I did it with the other formula. I'm not going to go through it, but here it is. If you would like to look at it and would like to do it, that's terrific, but it's here in writing for you. So, but you see how every one of those calculate. I didn't have to have the x squared values, but those weren't hard to get. Obviously, you just put them in a calculator and square them. Look at each number has to subtract the mean. I don't like that, but if you like it, I'm happy for you. But I don't like doing all that. I'd rather do it the other way. But it works. That's the key. So you see, I put it in the calculator box. Look at that. It worked beautifully and got 18.12. Now here's another one where I just use the fractions as probabilities. That's okay. Don't worry about that. Same idea. So I went ahead and left them as fractions and then converted to decimals. I thought it'd make it easier since they had a common denominator. So I took, did them all as fractions, got 46 over 11, then made it a decimal, 4.182. Okay, so I did it the way that I don't like right here. There's all that mess. I didn't like all that subtraction. And then, but I got 5.785. And then the standard deviation would be the square root's 2.405. And then use the mean again and did it my other way. I don't know why I reversed the order. I mean, I wasn't trying to confuse anybody, but why I use the other formula first, who knows? I might not change it around. But here, see there my x squareds right there. And so you see I went x squared 1 times 3 over 11, 16 times 4 over 11, 36 times 3 over 11, and 81 times 1 over 11 minus the square of the mean. I get 5.7836. See, that's just rounding, you know, 5.785 versus 5.7836. That was just that's a little more precise probably, but that doesn't matter. There's no way you would miss a question because of that. But close enough. And standard deviation, and there I mentioned it right there, is the rounding of the mean. Okay, here's another example that you can try if you want to with one or both formulas. Other than that, that will end this section on discrete probability distributions.